Well, so then you're not going to be able to switch.
No, but it's just
We're actually moving on to problem 5. So
I never looked up these.
I don't know what group was doing problem 5.
Wait, you don't
I'll take it.
That's the only one. So probability set 2, problem 5. How do we do that one? So one thing I do want to communicate is that in problem 4, one of the major differences besides the with replacement and without replacement, we had independence. Right? Once we replaced it and picked again, the first choice had no bearing on the second choice. It's like we were reset the whole thing. In 5 though, not so. Dependence is actually an issue in problem 5. Hopefully you appreciate that. If you get, for example, a red ball first, it actually affects your chances of getting a red ball second because your sample space literally changes. So the probabilities are affected here. But you might not notice, and I'll hopefully when I hear the solution we'll kind of figure out why. So in problem 5, how did we do that one? Yeah.
So problem for part A, it was 0% just because there's only one gradient.
Yeah, that one makes a lot of sense because you can't. So let's just remind ourselves the situation. So we have 10 balls in a bowl. We have 5 red, 4 blue, 1 green. Okay, and so A probability. So you select it and you don't replace it, and then you select again. So the probability of 2 greens. That's 0 because there was only 1. So if you actually picked a green in the first case, you can't actually pick the green again. So that's kind of that's straightforward. That one was nice. Probability of 2 blues. How'd you do that?
We did 4/10 times 3/9, so 4/10 is 4 blue out of 10, and then it's 3/9 because you picked one of the blues, so there's now only 9 and only 2 blues.
Okay. Why did you multiply? Yeah.
Would it be like if you were looking at like a tree diagram, kind of think of it that way? First branch would be 4 out of 10 odds, and the next branch off would be 3 out of 9.
And so you multiply along the arms?
Yeah.
That's one way to think of it, sure. Another way to think of it is, why multiply? Because we know that we multiply probabilities when we have independence. Why were we allowed to multiply here? This is in fact the right answer, but I don't want you to not appreciate why multiplication was the thing to do here, even though we don't have independence. The tree diagram is one way to think about it. Diagram. Another way to think about it is to think conditionally. So recall that if I have probability of A given D, this is the probability of A and B divided by the probability. The thing is, I can actually solve this for and write and as a product of probabilities where one of them is a conditional, so it's not really the original. In other words, what we're actually using here is we can think of it as a probability of the first blue and the second blue. And that's more like us thinking the probability that the second is blue given that the first was blue times the probability that the first was blue. So the multiplication that's happening here, it's actually this multiplication, not it's not the P of B1 times P of B2, it's actually a P of B2 on the condition of B1 times the P of B1. To get the first and the second blue means you get the first blue and the probability that the second is blue, given that the first one's blue. This one is the guy with the sample space of 9. And this guy was out of a sample space of 10. Right? So you're actually in two different situations here. One of them is actually a condition. So this here is it's actually a conditional probability. So yes, multiplication is the way to go here, but I don't want you to think it's because independence, because in this situation you actually don't have independence. You actually change your sample space. But it turns out multiplication, because of the formula for conditionals, kind of ends up being the thing you have to do anyway. Yeah, think of it, there were 4 choices out of 10, and now there are 3 choices out of 10, and I'm allowed to multiply those because of that formula. C. Same color. How'd you do that?
We did 5 over 10 times 2 over 9, so that's the probability that they're both red.
Okay.
And then we added the probability that they're both blue, so 4
Okay, so you did both red plus both blue
Yeah, plus both green, but that's 0.
plus both green. Now, like in problem 4, we do have mutual exclusivity here. Oh, mutually exclusive. You can't have several of these happening at once because that would mean you picked 4 as opposed to 2. So that allows us to add, right? So that's why we could have added here. So these describes 3 different situations. Yeah, and so red means you pick 5 out of 10, and on the condition that you did that, there were 4 out of 9 left for red. Blue, that was 4 out of 10, and 3 out of 9, and there that was 0. Which, by the way, one way to know that this was 0, you could just use your common sense, but also you could say, oh, there was 1 out of 10, but then now there's 0 out of 9, right? And you get the 0 that way, just by thinking in the same logic. So that leaves us with 20 over 90 plus 12 over 90, 32 over 90. And probability of different color. How do you do that?
So you do it kind of similarly to like listing your possibilities. So you do 1 times 10, 1 over 10 times 5 over 9, which would be, so if you're picking a green and picking a red,
Okay.
and then you do it as if you're picking a green and picking a blue, and then you doing it as if you pick a blue and pick a red. And then you multiply those 2 together and you add. So
Yeah, but you'd have to do the other way too, right?
yeah. You just do all that.
So blue first and green.
Yeah.
You could. There's another way. There's an easy way. You want to see an easier way? Yeah.
Could you just subtract the probability of the same number?
Yeah. Same color is complement of different color. To get different color means you did not get the same color. So that basically means the probability of a different color is going to be 1 minus the probability of the same color. Because these are disjoint events, and together they comprise the entire sample space. You'll either get a same color or a different color. These are the only 2 possibilities that can happen, and they are disjoint. Therefore, they are complements of each other. So I'll just actually subtract the answer from the previous one. So that'll be 8 over 9. which ultimately if you did it the other way by listing all possibilities, you should get the same answer, but it would be a lot more work. Moving on, any questions? So it's this kind of problem, choosing from something where the objects are distinct, is a very common type of problem. So you can expect something like this, I guess, on the next round of practice problems and or tests and or final. Problem 6. What group did problem 6?
We did.
Alright, so business majors are required to take Math 1108 and Math 1109. Suppose on average 15% of students get an A in Math 1108, while 10% get an A in 1109. 23.5% get an A in one course or the other. What fraction of students gets an A in both courses? How did you guys figure that out? What did you try?
Okay, so we used the, like the general equation that you gave us
Oh, yeah?
was,
What?
So we use the equation of P union, A union B, which is equal to probability of A plus probability of B minus the probability of A plus B.
Okay.
And we plugged in the numbers.
Okay, what did you call the A and B? Well, maybe A and B would be confusing because we're talking about getting an A in a class, so let's actually use different letters here. Say X and Y, X, Y, X, Y, where X is, set of students with A in 11 and 8, and Y means A in 1109. So we know the probability of students who get an A in one or the other is
0.015. So sorry, 0.15, sorry, 0.15.
no, it's this one. 23.5? It's the 23.5% of students get an A in one course or the other, so that's the or it's telling us about. So that's 0.235. What's the chances a student gets an A in 1108?
0.15.
That's 0.15. A in 1109, 0.1. This is the fraction of students who get an A in both courses. That's what we want. So I don't know what that is, and I can just solve for it. Get an A in first and the next course is going to be 0.15 plus 0.1 minus 0.235, and that is 0.015?
Sorry, I gave you the answer.
Huh?
I gave you the answer at the start
Yeah.
of accident, yeah.
0.15. So roughly 15 out of 1,000 would be the fraction of students, but you can write that. That was part A. Yeah, law of disjunction, nice one to do here, because you were told all the pieces. You were told this, this, and that, and you can solve for that other one. What is the probability that a student that gets an A in 1108 will get an A in 1109? What are we looking for here?
we used the base rule.
Base? How? What were you looking for?
So what are the odds of them getting A in 1108 given that they have an A in 1109?
Probability of that they will be in group Y given that they were in group X. So that's what we're searching for. And how did we find that?
Someone just walked in.
Oh. Yeah, I missed it. Okay. Face this one. Yeah, what is this? Y given X. How are you finding it?
Is it a base thing?
Well, you could do Bayes. Would you want to? I don't think you need to.
Is it just like the probability of A intersection Z over the probability of A?
Use that one. That's the general probability. So Bayes' rule is cool, it is important, but in general, you want to think simpler before you go to complicated. Bayes' rule is going to have all this other stuff. You'll need a lot of other conditionals for Bayes, right? Because you'll need the probability of X given Y times the probability of Y divided by all that whole stuff. That's a lot of stuff. We don't need it. We can just use the general definition here, and we have all the pieces for it from part A. So we know that X and Y is 0.015, and the probability of X is 0.15. And you can increase this to the right, and that gives you 0.1. 0.1. C. Is getting an A in Math 1108 and Math 1109 independent? What do you guys think?
The probability of A, given that B occurs, is the probability of A.
So we want to know that is the probability of Y, given that X has occurred, equal to the probability of Y? I don't know whether that's true. This one we found that was 0.1. This one we found, well, we were given, that's also 0.1. So the answer is yes. They're independent. I've had students tell me, well, it depends on the teacher you got, and if you did good in this class, you might. No, you don't want to go into that sort of reasoning. When you're talking about independence, let the numbers tell you. You have to either show that that is going to be working out, or one thing you could also do is to show that the probability of X intersect Y is actually the product of the probabilities. So you can check this equation, whether that's true. And they should both give you the fact that they are true. And that means, yes, independence. If they don't work out, no, they're not independent. How we check independence is one of these two equations. Either the conditional, doesn't matter whether it was the conditional, or the intersection is the product of the individual probabilities. Let's move on to problem 7. So, did anyone actually get to problem 7? Any group? Yeah? So everyone just turned in their answers and no one remembers what they're doing. Okay. Okay. Let's solve it together then. But first, just to kind of show you where the pattern is coming from. I didn't really see what you guys did, but I kind of saw what Nick's group was thinking. Are you in Nick's group? No. Yeah. And they ran into the problem of having things in a certain order. So let's actually do that. Let's do an easier version of problem 7 because I want you guys to see where these numbers are coming from. I'm kind of going to use this as an excuse to segue into another kind of probability. So let's look at this together and then we'll go through and solve problem 7. So suppose the number of attempts instead. So same situation. We have a basketball player that we know makes 70% of his free throws. He attempts 10 of them, and they're all independent. What is the probability that he makes all 10, or makes exactly 2, or makes between 3 and 5, or makes at least 1? So let's make that smaller. Let's say he makes 3 attempts, not 10. And probability that he makes 2. So let's actually reason through this. How would I find the probability that he makes 2? What would you think about it? Yeah?
Well, I wouldn't say the order doesn't matter here, right? Because you can choose whenever. So just think about it in terms of like the spots. Like 2 of them, you have like a 70% chance, while the other.
Okay.
not
So you're gonna think in spots,
Yeah.
like stages, right? So
Yeah.
he's making three throws. Let's think of them in stages. So there's the first free throw, the second free throw, the third free throw. Okay. So what can happen?
The first one, let's say like he makes the first one, so that's a 0.7%.
Okay.
0.7.
So he makes the first one.
Second one, same. Third one, same.
He makes the first one.
Makes the second one. Makes the third one.
Well, how can he make the third one?
Oh, it's only 2. Okay, so it makes it 2.
We're focused on probably that he makes 2, which means if he makes the first 2, he's gonna miss the third. So that is one possibility, right? So you can come up to the line. Right, yeah, that's what I'm supposed to do. Yeah, and he gets the ball in. Then he starts feeling full of himself and then not even looking, then he misses, and then a voice in the stands goes, "You suck!" Right? So that's one way that can happen. Okay? What's another way that this can happen?
You could miss the first one and get the next 2.
Yeah, you can miss the first one, accident comes up. It's visibly kind of shaken, misses it, starts feeling down on himself, starts hearing those voices in his head from his past. "Man, you ain't nothing, you're never gonna amount to nothing, you suck." And the voice in the stands comes out and he's like, "We believe in you!" And he has a renewed sense of fear. And that's another way that can happen. Great. The other way. That's a possibility. You should have thought of that possibility. The other way is like he comes up, hey, he's okay, he's alright, he's comfortable. Alright, makes the first one. Okay. Gonna make the second one. Free tacos! Who said that? Dude, I'm trying to shoot here. Okay, so he misses the second one. Okay, he makes the third one. Alright, that one's not so cool. Those are the ways that this can happen. How many ways could that happen?
3 ways.
There's 3 ways. How would you know 3 was the answer? Why is 3 the answer? How are you thinking about that 3? I mean, what if it was making 100? Like, what were all the variations?
Is this some kind of permutation?
Is it a permutation?
Order matters.
Order doesn't matter, right? So how would I actually pick? I just care that he makes 2. I just care that when I look on these experiments, I see 2 green checks and 1 red X. I don't really care what order. Any of these situations would count, right? So it's not like he has to make the first and the second. He could have made the second and the third, or he could have made the first and the third. How do I count how many ways that could have happened? Yeah?
Is multiplication.
In what sense? No, the multiplication rule would tells you the total possibilities, the total number. Yeah?
I would just do, alright, so I got 2 checks, that's 0.7, and I got 1.
No. I'm talking about the total number of ways that you could have gone.
I don't know.
How do I know there were 3 ways? How do I know there wasn't another possibility that I didn't see? How do I know I got all of them?
Because those are the 3 possible orders that it can happen. That you just know. Like
You just know? Okay, he's making 1,000 shots. How many ways can he make 735 of them?
well, we're using a smaller.
I know, but the point, I want you to be able to see how you would count the small ones. Come up with a general strategy here. That doesn't depend on the fact that we're only looking at 3 attempts. Huh? No, permutation would mean the order matters. I don't care what order he makes the 2 shots in, I just want to know if he makes 2 shots.
It's a combination.
It's a combination, that's the only other one, right? It's actually 3 choose 2. I want to choose the 2 shots that he's going to make, right? There were 3 shots that he's attempting. I want to choose 2 of them that he's going to make. He can make either the first 2, or the last 2, or the first and the third. But if you were to extend these numbers of possibilities and extend the number of successes I want, I can just use a combination. There are 3, this by the way is 3, right? So he's going to make 3 attempts. I want to know how many ways can he get 2 of them. How many ways can we select 2 shots to be the successful shots? So that should kind of hint you how we're going to deal with it when there are 10 situations. I don't want you to have to write down 10 slots all the number of times and try to figure out how many ways can I get 2 checks. That's going to be too time consuming. Think of it as a combination. There are 3 positions. I want to pick 2 of them to put checks in. Okay? Now let's look at the probabilities. What is the probability of the first situation? Huh? No. What is the probability that he actually makes the shot?
70%.
Okay.
70.
So it's 70% times 70%
Times
0.3. Why can we multiply them? Because they're independent. We were told he makes all the shots independently. So if he's going to make this 3 combinations, I just multiply them to talk about that's how it could have happened. So this is going to be 0.7 squared times 0.3. What about this one? Well, it's going to be 0.3. That's going to be 0.7. That's going to be 0.7. And it turns out that's also 0.7 squared times 3. This one is, spoiler alert, it's going to be 0.7, 0.3 times 0.7. That is going to be 0.7 squared times 3. Now, because these are mutually exclusive situations, he can't make the first and the second and make the second and the third. That would mean he makes all 3. These, to find the total probability of one or the other, right? These are all the ways that he could make the 3 shots. Well, I'm going to add all these guys. So I'm adding this same expression, 0.7 squared times 0.3. How many times? Well, there are going to be 3 choose 2 of those combinations. In other words, that's 3. 3 times 0.7 squared times 0.3. That is going to be the probability that he will make 2 out of the 3 shots. Do we understand the reasoning here? Yeah.
Do we ever run into a situation where the different scenarios don't have equivalent probabilities?
No. That would be a different situation entirely. This is a very specific situation, and it is called. Let's actually generalize this a little bit, and then I'll tell you what it's called.
Well, you said you wrote 3 choose 2 over here times 0.7?
Yeah, because that's how many times I'm adding these things together, right? I add this number 1, 2, 3 times.
Gotcha.
Why did I add it 3 times? Well, that was the total number of ways it could have happened, right? So that kind of tells you, hint, hint, if there were 10 choices and I wanted him to make 2 shots, it would be 10 choose 2. I would have 10 choose 2 of these lines that I'm adding together. And I would multiply this expression by 10 choose 2.
Okay.
Right?
So you're
So-
getting like the individual probability first?
Yeah.
And then,
Well, you think of it that way with a very small example, and then you generalize that for bigger examples. So once we figured out how this works with 3, it's going to work the same way with 10. It's going to work the same way with 1,000. It doesn't matter. There's going to be n choose 2 ways that he could make 2 shots out of n shots, right? All the probabilities of those individuals, because of independence and multiplication, doesn't matter the order, they're all going to give us the same probability. And I'm just adding that probability with the number times the number of different situations. Yeah.
Is that why, like, as you take more and more shots, it's eventually going to sum towards 0.7? Because there's going to be more and more lines for it to, like, add together, or whatever that probability is.
I wouldn't say it sums to 0.7. It will approach 0.7 to the end.
Yeah.
Yes. So let's actually start generalizing this a little bit, because it's a whole new kind of probability. It's a very specific situation. So, to generalize. Suppose he made n attempts, and we want the probability he makes, let's say k of them. Then, and also let's say P is the probability he makes the shot. Let Q be the probability he misses the shot. Then what I'd be able to say, the probability that he will make K of them is going to be by the same reason, it is going to be n choose k times p to the k. Notice I want the success to happen k times. So the success happens 2 times. That tells me the power. That tells me how many times I'm multiplying that probability. Times the q also to a certain power. Now what is that certain power? Well, it's just going to be all the leftover times. That's n minus k. Now, this is called, does anyone see it from that formula?
Is that binomial?
It's binomial. This is called a binomial probability.
Are we doing expected value?
We are going to do expected value.
Are we going to do geometric?
No.
Good, thank God.
So I'm going to talk about this, to talk about expected value, to talk about probability distribution, so you understand it as an idea. And then I'll just mention, there are other ones out there, like geometric and Poisson and all that other stuff. But once you understand the idea of how a binomial works, you will, in principle, understand how the others work. So the others will work in the same way the binomial works. The difference is they will each have their own specific formula. For the binomial situation, this is the formula. Now the binomial situation, the bi is the root word here, which means 2. Basically, you're looking at an experiment where there are 2 options, which you think of as success and failure. So here's the situation. Here's how you can read a random probability problem and know that you're in a binomial situation. There are 3 conditions that you look for. One, an experiment is being repeated n times. You're doing the same thing n times. Two, there are only 2 possible outcomes. That's why it's called binomial. Success or failure. 3, each outcome is independent. So if you're reading a word problem and you realize that this is fulfilled, the same thing is happening over and over and over again, and there are only really 2 ways this can go down. What is the probability that it will go one of these ways a certain number of times? If we assume they're all independent, you will say you're in a binomial probability situation. It's very specific. These 3 specific things must occur. Then, if P equals the probability of success. Now success can mean, it's just the thing you're looking for, right? It could actually mean something bad technically. Q is the probability of failure. Now because it's only two options, success or failure, this is of course going to be 1 minus P. So once you figure out the P, you know what this one is going to be. And K is the number of successes we want. Then, and let X be a variable. This is going to allow me to introduce random variables. Let X be the number of successes that occur. Then the following formula will apply. The probability that X is K, that X equals K, this will be NCK P to the K Q to the N minus K. And that you know how to do in your calculators. So this is called a binomial probability. A situation where you have these three things happening, and using these variables, I can actually find the probability of any one of those. It also stands to reason. If I want the probability of, say, X between a certain number. So there was a question of, oh, what if he makes between 3 and 5? As an example. If he makes between 3 and 5, what does that mean? Well, that means he would make 3, X equals 3, or X equals 4, or X equals 5, which here we automatically have mutually exclusive here. This is the probability that X equals 3 plus the probability that X equals 4 plus the probability that X equals 1. And for each of these, I can use this formula. If I had another situation, and after this, what I want you guys to do is actually attempt problem 7 and come to the answers tomorrow, and then we'll move on from that. If I want the probability that X is at least 1, that is just the probability that X is greater than or equal to 1. That's what at least means. By this idea, that means that's the probability that X equals 1 plus the probability that X equals 2 plus, and that could go on for a long time depending on how big N is. So rather what you want to do is you want to do the complement. Just think of it as 1 minus the probability that X is less than 1, which now is literally only one situation. It must be 0. And you can use this formula to figure that out. Just put in 0 for K. So this is called a binomial probability. There is a standard way to deal with it, namely thusly. So you're in a situation where an experiment is being repeated. There are two possible outcomes. They're all independent. You are looking at a binomial probability. This is the formula that applies. So find the probability of your success, probability of your failure, the number of attempts, the number of successes you want, and that's how you can find an individual probability. Try problem 7. All right. See you guys tomorrow. Thank you.